Welcome to OOTO TV, the out of the office investigation from the past into the future of marine navigation and autopilot technology. This time, we're discussing the requirement specification for a marine navigation and piloting tool for both inshore and offshore global navigation. I'm Captain John Paul Jones, and with me is Skipper Grace O'Malley. Grace, we've got a fantastic journey ahead of us today. We're going to construct a blueprint, really, for these incredible navigation systems. We'll start with the big picture, the massive challenges navigators face out there. Then, we'll dive into the physics of it all, waves and speed. After that, it's all about finding our place in the world with positioning systems. And from there, we'll build up to how technology creates total situational awareness on a modern integrated bridge. And finally, we'll take a peek into the future. It's going to be quite the build-up.
It really is, John. And to understand why this blueprint, this requirement specification is so vital, you have to put yourself on the bridge of a supertanker. Imagine it's pitch black, miles from any shore, and a storm is raging. The waves are just relentless, and visibility is practically zero. Every single decision, every course correction depends completely on the information glowing on those screens in front of you. The trust in that technology has to be, absolute. This is the grand challenge, engineering a system that simply cannot fail.
Absolutely, Grace. Look at that image. In conditions like that, there is zero room for error. A tiny software glitch isn't just an inconvenience that makes you restart the system, it could be a catastrophic failure. We're talking about a potential grounding, a collision, an environmental disaster. That's why this document we're investigating, the requirement specification, is so unbelievably critical. It's not just a list of cool features. It is a life and death contract between the engineers who build this stuff and the crew who bet their lives on it every single day. So that's the big question, right? How do you actually engineer that level of absolute safety and efficiency? And the answer, the core of our discussion today, is this foundational document, the Requirements Specification, or RS. You have to think of it less like a simple product manual and more like the architectural DNA for the entire navigation system. It dictates every single thing the tool must do, how well it has to do it, and the punishing set of standards it has to meet before it's even allowed on the bridge of a vessel. Exactly. And any robust requirement specification has to be clearly defined and built on three unbreakable pillars. First, you have to know your audience and their needs. The captain of a small coastal fishing boat has vastly different requirements than an officer on a massive LNG carrier. Second, you have the core technical requirements, the raw performance specs, the nitty-gritty of how fast and how accurate it has to be. And third, you have the safety regulations and restrictions. These are the non-negotiables set by maritime authorities. If you get any one of these pillars wrong, the whole structure is compromised. Okay, now this is where we get to the really cool part, John. Before we can even begin to think about the software or the flashy screens, our entire blueprint has to be grounded in some fundamental physics. It all starts with understanding these invisible waves that connect a ship to the rest of the world and, fascinatingly, allow it to measure its own motion through the water. Let's start with radio waves. The term propagation sounds complicated, but really it's just about how signals get from point A to point B. For example, lower frequencies are great because they can literally hug the curve of the Earth, which makes them perfect for long-range communication systems. On the other hand, higher frequencies like VHF are more line of sight, so they're ideal for short-range data links between ships. The physics itself dictates which tool is right for the job, and the RS document has to specify exactly which frequencies the equipment must be able to use. And here's where the real-world engineering challenges kick in, Grace. As you can see in this diagram, signals don't just travel in a nice, clean, straight line. They bounce off the surface of the water, they reflect off the atmosphere, and the ship itself, which is this massive chunk of steel, acts like a giant electromagnetic screen. It creates all kinds of interference. This makes the placement and design of antennas an incredibly critical and often frustrating part of the whole design specification. Get it wrong, and your multi-million-dollar system is deaf. So true. Now, let's switch from waves in the air to waves in the water. Because to know where you're going, you first have to know exactly how fast you're moving. And the key to this is the Doppler principle. We've all experienced this. It's that classic change in pitch of an ambulance siren as it screams past you. As it comes towards you, the sound waves get compressed and the pitch sounds higher. Then, as it moves away, those waves stretch out and the pitch drops. It's just a fundamental law of physics. You're listening to OOTO TV with research by author Paul Bulow. And what's absolutely brilliant about applying this on a ship is that we're not just measuring one speed. Look at all the vectors in this diagram. By using multiple angled beams of sound that bounce off the seabed, a Doppler speed log can calculate not just your forward speed, but also your sideways drift, your transverse speed. This gives you a complete velocity vector, a full picture of your motion, which is absolutely essential for tricky maneuvers, like docking a massive ship in a heavy crosswind. All right, so our blueprint is really starting to take shape. We've grounded it in the laws of physics, we can measure our speed accurately. Now we get to the next piece of the puzzle, and it's arguably the most fundamental question in all of navigation. Where on Earth am I? This is where the technology becomes truly astounding. You know, for decades, the absolute gold standard for this was Loran-C. It was a really clever ground-based radio system. I remember using it. It was reliable, especially for coastal navigation, but it had its limits. It was regional, you couldn't use it in the middle of the Pacific. Then GPS came along and completely changed the game. It essentially took those Loran transmitters and launched them into space, creating this incredible positioning grid that covers the entire planet 24/7 in any weather. The concept behind GPS is just so elegant, isn't it? It's both simple and genius at the same time. You've got this whole constellation of satellites orbiting the Earth, and each one is basically a hyper-accurate clock in the sky. It's constantly broadcasting its exact position and the precise time. Your receiver, down on the ship, listens for signals from at least 4 of these satellites, and by calculating the teeny-tiny difference in arrival time for each of those signals, it can triangulate, or to be more precise, trilaterate, your exact position on the globe down to a few meters. And the sheer amount of data packed into that signal is incredible. It's not just a simple ping. As this diagram of the data frame shows, the satellite is constantly sending its own health status, ultra-precise clock corrections, and its exact orbital path, called the ephemeris. But even with all of this amazing data, tiny errors can creep in as the signal passes through the atmosphere. And for navigating a narrow channel, close enough is not good enough. That's why we have enhancement systems like differential GPS, or DGPS, to refine that signal and give you hyperlocal accuracy when you need it most. So our blueprint is getting pretty sophisticated now. We've got the physics down, we know our speed, and we know our precise location. The next critical question becomes, what's around us? This is the whole world of situational awareness, and it's where we transform all that raw data into actual life-saving knowledge. And the absolute foundation of situational awareness is the chart. Now, for a long time, digital charts were just scans of the paper ones. We call them raster charts. They looked familiar, which was nice, but to the computer, it was just a static picture. The real revolution, John, was the vector chart, or ENC, Electronic Navigational Chart. This isn't a picture, it's a database. Every single buoy, every depth contour, every inch of coastline is a distinct object with data attached to it. The chart is now intelligent. And because that chart is now intelligent, the system that displays it, the Electronic Chart Display and Information System, or ECDIS, can be intelligent too. This is so important. It's no longer just a digital map. It's an active safety system. The ECDIS takes your GPS position, fuses it with that smart chart. It monitors your planned route, and it can sound an alarm if it calculates you're heading towards danger, like shallow water. It incorporates these existing databases of charts and maps, noting passages, obstacles, and traffic, and it's constantly watching your back. And one of the most crucial layers of data fed into that ECDIS is the Automatic Identification System, AIS. What a game changer this was. Every large vessel is continuously broadcasting its identity, its position, its course, and its speed over VHF radio. Your ship receives all this data, and the ECDIS plots every single vessel around you on the chart in real time. Suddenly, a crowded waterway isn't just a screen of anonymous radar blips anymore. It's a dynamic, clear picture of identified traffic. Collision avoidance improved tenfold overnight. So let's just recap how this all builds. We have GPS for position, a Doppler lug for speed, ECDIS with smart charts, and AIS for traffic awareness. For years, these were all separate boxes with their own separate screens on the bridge. The whole concept of the integrated bridge is about tearing down those individual silos and fusing everything, absolutely everything, into one seamless, cohesive command center. You're listening to OOTO TV with research by author Paul Bulow. And that brings us to a really critical question, John. It's one thing to talk about this concept of integration, but what are the key technical elements for implementation on the bridge of both small and large vessels? How do you actually get all this different equipment, often from different manufacturers, to work together flawlessly? The answer, Grace, is standardization. It's the only way. You might have a radar from one company, a GPS from another, and a gyro compass from a third. To make them all talk to each other, you need a common language.
That's where data protocols like NMAA 0183 and the more modern NMAA 2000 come in. They are the universal translators. They define the exact sentence structure for how every single piece of equipment reports its data. Without those standards, the integrated bridge is just a collection of very expensive, very silent boxes. And this flowchart, wow, it gives you a little peek at the insane complexity happening behind that deceptively simple screen. On startup, the system runs through this whole checklist of procedures. It's constantly processing data from dozens of sensors, managing alarms, and running self-diagnostics. All of this incredible processing power has one singular goal: deliver a rock-solid, stable, and completely reliable picture of the world to the navigator, every single second of every single watch. Right. And this brings us squarely to the human factor. You can have the most powerful, most integrated, most technically brilliant system in the world, but if the navigator on a grueling 12-hour watch can't use it effectively, it's a failure. So this leads to a vital question. What features are required for a modern and high-quality user experience? How do we present this fire hose of information in a way that is clear, intuitive, and actually enhances decision-making, rather than causing information overload? That question is the perfect transition to our final section, John, because as we look to the future, we realize this blueprint for navigation isn't carved in stone. The requirements specification is a living document. It's constantly being redrawn by new technology, especially in connectivity and automation, which in turn is completely reshaping the role of the human on the bridge. Which leads us to our final and perhaps most important question as we look forward. Can users connect to both integrated sensors and connected databases through Starlink, satellite, and VHF, as well as other radio frequencies that deliver real-time weather and navigation data? What happens when the ship is no longer an isolated island of data, but is instead constantly connected to the cloud? The answer is, it changes absolutely everything. This constant, high-bandwidth connectivity is the engine of a whole new maritime data revolution. It means your charts are no longer updated by a CD-ROM you get in the mail every few months. They can be updated instantly, over the air, in real time. It means you can download incredibly detailed weather models to optimize a route for fuel efficiency, avoiding a storm before it even forms. It could even allow an engineer sitting in an office in Hamburg to remotely diagnose an engine problem on a vessel in the middle of the South Pacific. And this really brings a crucial point home. The blueprint is never finished. The requirement specification for marine navigation tools is a living document. It has to be. As soon as a new technology like Starlink becomes viable at sea, or a new international safety regulation is passed, the RS has to be updated and evaluated on an ongoing basis. It's a perpetual cycle of refinement, always pushing for a safer, more efficient, and more capable system. And this quote just brings our entire investigation full circle, doesn't it, John? After all the talk of DOTA and satellites and software and protocols, it all comes back to the human factor. Because as these systems get more powerful and more automated, the role of the skilled, vigilant navigator on the bridge becomes even more critical. The ultimate requirement, the ultimate goal of the blueprint, is to build a tool that empowers human judgment, not one that tries to replace it. What an incredible journey from basic physics to the future of shipping. Thanks for joining us on OOTO TV.